Welcome to lecture 5.3 on logarithmic functions and graphs. This is a picture of me in the Great Smoky Mountains outside Gatlinburg, Tennessee. Great trip, and there's some great driving parkways there to see awesome scenery. So today we're looking at logarithmic functions and graphs. We're going to find common logarithms and natural logarithms with and without a calculator. We're going to learn how to convert between exponential equations and logarithmic equations. We're going to learn how to change the logarithmic base. We're going to learn how to graph log functions. And we're going to solve an applied problem involving log functions. Some common log functions are the Richter scale is a good one. And also carbon dating is an exponential / log function as well. Log functions are inverses of exponential functions. So we can draw the graph of the inverse of an exponential function by interchanging x and y. We learned this in the first sections of this chapter, both about exponential functions and then about inverse functions. So for example, to graph x equals 2 to the power of y, we're going to choose values for y and then compute values for x, and then we're going to plot them in reverse. And so here's a table of values. We just picked values for y and then plotted values for x, and then here's our graph. Note that the curve does not touch or cross the y-axis, okay? And this will be important about limits on the domain of a log function. This is essentially the graph of a log function, and we'll see something in a minute to that effect about how x cannot be negative here. Okay. So you can see that this curve looks like the graph of y equals 2 to the power of x, and it's reflected across the line y equals x, as we would expect for any inverse. The inverse of y equals 2 to the x is x equals 2 to the y. Again, from the last section, we saw that we just swapped out and interchanged x's for y's and y's for x's and vice versa. So the gray line here is the exponential, and the red line here is essentially the logarithmic graph. Logarithmic function. We define y equals log base a of x as that number y such that x equals a to the power of y. Where x is greater than 0, again, this is that idea that you cannot take the log of a negative number as we saw in the graph, and a is always a positive constant other than 1, okay? We read log a of x as the logarithm base a of x. Logarithms, as we saw from the graph, are inverse functions of exponentials, just as subtraction is the inverse function of addition. Okay, so you can see here on the left you have an exponential, 3 to the power of 4 equals 81. We can write that in terms of a log. Log base 3 of 81 equals 4. Notice we have the same three parts, a base, an exponent, and an answer. Log, the base stays the same, of the answer equals the exponent. Here I've just put in variables so you can see that as well. Base to an exponent x equals y, which is the answer. The base stays the same, so log base b of the answer y equals the exponent. And here it is in language. Base raised to an exponent equals an answer. Log of that same base of the answer equals the exponent. So a log is actually an exponent. It's the exponent. It's the way we undo exponentials. To solve logarithmic problems, probably one of the easiest things to do is to convert to an exponent and then calculate. Remember this, log base of the answer equals the exponent. we can convert these same three parts, base, answer, exponent, into an exponential. Base, exponent equals the answer. So let's look at an example. Log base 2 of 16 equals x. Okay. So our base is the same. It's going to be a base 2. Our exponent is the answer to the log. We put that as the exponent, and then this equals 16. So if I'm trying to figure out what the log base 2 of 16 is, I convert it to an exponential, and then I figure out 2 to what power equals 16. Well, that's 4. I could have just wrote out number 2 times 2, and that's 4 times 2, and that's 8, that's 3 2s, and times one more 2 is 16, and I can see it that way. So without using a calculator, evaluate each of the given expressions, okay? So again, what I want you to do first here, and hit pause after I explain this, is to convert the log to an exponential equation and then see if you can find or solve for x what the exponent should be. So here notice we don't have an answer, so one of the first things we're going to do is to plug in equals x in these. So then we have the three parts. We have a base, an answer, and an exponent. So for number 17, we're going to convert it to 4 to the power of x equals 64. And then we figure out that 4 times 4 times 4, or 4 to the power of 3, is indeed 64. Now see if you can do these other three problems that are here by hitting pause and then moving on. 18 is 5 to the power of x equals 125, and we get x equals 3. 19 is a little confusing. So we get 2 to the power of x equals 1/4. Well, remember that 1/4 is 1 over 2 squared. 1 over 2 squared. And remember, we can take the 2 squared in the denominator to the numerator by changing the sign of the exponent. So 1 over 2 squared is the same as 2 to the negative 2. And then we see that we have 2 to the x equals 2 to the negative 2, so the exponents have to be equal. Similarly, with 20, we can see here that 3 to the x equals 1 over 27. Well, 27 is 3 cubed, so we have 1 over 3 cubed, or 1 over 3 cubed is the same thing as 3 to the negative 3, so the x has to equal negative 3 here. So do the same thing here. We're going to do the same kind of process here. We've got 6 more examples for you to try. I'm going to run through these really quickly. I suggest you pause right now and see if you can find all of the answers to these 6 problems. So hit pause and try these on your scratch sheet or in your notebook, and then hit play again. Remember that you're going to add equals x to each of these problems so that you have 3 parts: a base, an exponent, and an answer. So we're first going to convert each one to an exponential. So for a, we get 10 to the power of x equals 10,000. Well, this is x equals 4, right? 10 times 10 times 10 times 10 is 10,000. For b, we have that kind of fraction thing again. It's a decimal, and it's usually helpful to put the decimals into fractions. So we're going to do that. 10 to the power of x, again, base, exponent, answer, equals 0.01. Gives us x equals negative 2. Remember, 0.01 is 1 over 100. This is the same thing as 1 over 10 squared, or 10 to the negative 2. And so you can see if 10 to the power of x equals 10 to the negative 2, then x has to equal negative 2, because the bases are the same. For c, we have 2 to the power of x equals 8, which gives us x equals 3. 2 times 2 is 4, times 2 is 8. For d, we have 9 to the power of x equals 3. This gives us x equals 1/2. This is another challenging one, okay? Remember that the square root of 9 is equal to 3. Well, and we can rewrite square roots, or any root or radical, as a fraction exponent. The square root of 9 is the same as 9 to the power of 1/2. And so we get 9 to the power of x equals 9 to the power of 1/2. So we know that the x has to equal the 1/2 because the exponents need to be the same. For e, this is something we learned earlier, or actually we didn't learn this earlier, but c to the power of x equals 1. 6 to the power of x, equals 1. And this gives us x equals 0. Now why is that? Remember that anything, any number, any variable to the 0 power equals 1. So whenever you're taking the log of 1, it doesn't matter what the base is. This could be 6, it could be 9, it could be 10, it could be 2. If you're taking the log of 1, the answer is always 0. Because any variable raised to a 0 exponent equals 1. And the last one, we get 8 to the power of x, 8 exponent x equals 8. Well, this is going to be x equals 1, because 8 to the power of 1 is going to be that same number. And so whenever we're taking the base, the log of the base, when the base and the answer are the same, the answer will always be 1, 2. 1 as well, not 1, 2. Okay? So these are two fundamental rules. Whenever we take the log of 1, this will always be equal to 0, no matter what the base, in this case, a is. It doesn't matter what number is there. And whenever we're taking the log of the base, when the base and the answer match, the answer will always be 1. And this, again, is for any logarithmic base a. It could be 1, 2, 3, 4, 5, 6, 7, negative. Actually, it can't be negative. Remember, it can't be 1 and it can't be negative. Sorry, my bad. We've already learned that log base a of x equals y can be converted to an exponential expression that's equivalent, which is x equals a to the power of y. Okay? A logarithm is an exponent. A logarithm is an exponent. So let's see if we can convert these the other direction. Convert each of these exponentials to a logarithmic equation. Remember, base, exponent, answer. Base, exponent, answer gives us log of the same base. Answer equals exponent. Okay? So, excuse me, 16 equals 2 to the power of x is the same thing as log base 2 of 16 equals x. Remember, the exponent is the logarithm. You see that here in green. And the base remains the same. The base on the exponent is the base of the log. Okay? For b here, we have a base 10, log base 10 of the answer, 0.001, equals the exponent negative 3. And for c, we have e to the power of t equals 70 is the same as log base e, same base, of the answer, 70, equals the exponent t. Okay? It's very important that you can go back and forth between logs and exponentials, rewriting them in either form to be able to write an exponential as a log or to write a log as an exponential. Convert each of the following to an exponential equation. Again, we're just going to do the same thing in reverse. Here we have a base 2 of the answer 32 equals 5. Again, you might want to pause here and see if you can rewrite these. And on b and c, we just have variables. Okay? Again, the base remains the same, so the base 2 on the log becomes the base of the exponential. The logarithm is an exponent, so the 5 becomes the exponent, and our answer is 32. Here we have variables more than numbers, so we have base a to the power of 8, which is the exponent, equals the answer. Base a, power 8, exponent 8 equals q. Don't get confused by the variables. Here we have all variables, and we have x equals log base t of m. Our base is t, our exponent is x, and our answer is m. Okay? If you need to watch that again a little more slowly, that's fine as well. This is probably a good time to take a pause. We're about halfway through the lecture. You can just hit pause here and go get yourself a drink, or go walk outside, go do a little TikTok dance, whatever. But this is something that came across my phone recently, and I thought it's a really good one, about how it's really important for each of us to put ourselves first and to take really good care of ourselves. And so here are 10 ways to show up for yourself. Commit to habits, practices, routines, and rituals that are good for your well-being, even when you don't want to. And your habits are going to be different than my habits. Put first things first. What do you really want in your life? What is the experience you want to have on a daily basis and in your life? And think of the habits that will help you get there. For example, right now you're in college, and one of the habits that you need to have is a really disciplined approach to studying, blocking out times, etc. Number 2, allow yourself to feel a multitude of feelings without labeling it as wrong, bad, or negative. My kid's godmother always said, feelings make great guides, but horrible masters. When you're angry, your feeling is giving you an alert. It's like a security alarm for yourself. When you're angry, it's okay. The key is to figure out, what do I want to do about it? So it's a great guide. It's letting you know that something is upsetting you, but it doesn't mean you have to act on it. Think about it. If all the times we were angry while driving and someone cut us off, sometimes the reaction is, I want to wreck my car into them, right? Well, that's not a really good solution for me in the long term. So the feeling is okay, but what we do with it is what's important as well. But also recognizing that the feelings are there, they're there to help us. And anger does have a place. Anger can give you good energy. If you're being taken advantage of in a job or in a relationship, anger can give you the courage and the forcefulness to stand up for yourself in a different way. Number 3, practice listening to your needs and discovering different ways of meeting those needs. This is tough, especially nowadays with so many distractions. Our phones are the number one distraction. Social media, texting, etc. So it's hard to kind of really let that go and really listen to what do I really want? What do I really need? Where do I want to head? And we all struggle with this, and especially because the technology behind phones and social media is addictive. It's addictive on purpose. The phone's ding, it's like the Pavlovian dog. It's a conditioning. It triggers something in our brain and in our hormones that is like equivalent to, they say, eating chocolate. It's a reward system. So you really have to be conscious of this and possibly even give yourself a detox, a phone detox. If you can only do half a day, do half a day. If you can only do overnight, etc. Okay? Practice self-forgiveness for not being perfect, for forgetting, for your past, for what you don't know, and for getting off track sometimes. You will screw up. I will screw up. I will make mistakes until the day I die, okay? And being gentle with myself, trying to learn from those mistakes and do better is one thing, but beating yourself down does not help. We say we beat ourselves up, but we never beat ourselves up. We always beat ourselves down. Lifting ourselves up is a different way, and forgiveness is a way for that. Let yourself start again over and over as often as needed. And this just goes right with number 4. Forgiveness is the quickest way to start again. When you keep beating yourself down, it's hard to move out of that place. Take care of your basic needs. Stay hydrated, get enough sleep, move your body, and eat plentifully. This should be number 1 in my book. This is the easiest thing to do if we do it in a very simple way. You don't need to belong to a gym. You don't need to, exercise 6 or 7 days a week at the gym, several hours. One of the simplest things is just to go walking and to walk for an hour a day. It's not that far. You walk out your door, you walk in a neighborhood, you find a nice place to walk, you go to a park, you go to Katy Trail. But the easiest thing is to find a place that you can walk right outside your door. It clears your head, especially if you leave your phone off or don't always listen to music, etc., but just listen to yourself. Give yourself permission to rest, to take breaks, and have downtime. Very important, and especially in your situation right now in life with school. You're so busy, or you can be so busy, that if you balance that with breaks, you can be much more productive, and this goes forever. Spend quality time with yourself. What is it you really enjoy outside of television and your phone? Reading, writing. Find some creative outlet, whether it's decorating or cooking or painting or drawing or making something. and getting to know who you are underneath who you think you should be. Use a lens of curiosity and compassion with yourself as often as possible. Why did I do that? What was that about? Trying to be self-reflective and figure things out. Remind yourself that you are as worthy of being shown up for as anyone else, in life. Make yourself a priority in your own life. Even when you have other people that you are responsible for, a spouse or children, etc. I always think that what they say on an airplane is good life advice. If you're traveling with someone who's dependent upon you and the oxygen falls, make sure you put the oxygen on yourself first. Why did they do that? Because you could pass out while you're trying to put oxygen on someone else. And you definitely can wear out if you always put other people's needs first. It is important for you to recharge and to stay fully charged. Hope you enjoyed that. Hope you enjoyed the break. Now let's get back to logarithms. Find each of the common logarithms, base 10, on a calculator. You'll find on your calculator that there is a log button that's right to the left of the number 7. This is the common logarithm. It's base 10. It's called common because our decimal system, our numerical system, is a decimal or base 10 system. Okay? You'll notice that when we are talking about common logs, there is no number. There's no number at the base. Okay? So if there is no little number written after the word log, then these are common logs and they are base 10. So all I'm asking you to do is plug this into your calculator. For example, log 645,778, just plug it into your calculator and this is what you'll get. Okay? It says round to 4 decimal places, so we stop after the double zeros. And the next number is 8, so it's going to be 0.8101. Try the other two. You can hit pause and see what you get. These are pretty simple, but definitely try them. It's good practice. Okay? For the second one, we get negative 4.621602099, which we round to negative 4.6216. The log of negative 3, we put this in, and notice we get an error. You cannot take the log of a negative number. Now, why is that? Well, let's go back to the idea of the base. Remember, the log is the exponent. The base is a positive number. A positive number raised to an exponent. Remember, exponents say multiply that base by itself. A positive number times itself with another positive number will never give us a negative number. Positive times positive times positive times positive will always be positive. So you cannot take the log of a negative number. This will always give you an unreal answer, an undefined answer. And this is why when we were looking at the graph originally, it did not cross the y-axis, so you could not take showing that you couldn't take the value of any negative x values of logs. Okay? There's another kind of logarithm called natural logarithm, and you remember from our prior lecture about Euler, the mathematician from the 1700s, this is that Euler's number, e. And logarithms, base e, are called natural logarithms. Okay, and remember Euler discovered that this number e was occurring in nature in exponential equations. The abbreviation ln is generally used for natural logs, and you'll see right below the log button on your calculator you also have an ln button. lnx, it actually means log base e of x. Do not write log base e of x, use the abbreviation ln. And of course, the natural log of 1 is equal to 0, as any log of 1 is equal to 0. And the natural log of e, since a natural log is a base e, we're taking the log of the base, and that's always going to be 1. So it follows the same principles as we talked about before. All right, we're going to try this with your calculator again. I'm going to go through these really quickly and show them to you. But immediately before I do that, which one of these is going to have no answer? Hopefully you pick 6, because you see that we're taking the log of negative 5. Okay, so here we have all these answers. You can check your own. It's interesting, I'm sorry here, this should be the natural log. Why it's the common log, but in either case it wouldn't have an answer. And there's our 5 answers. Again, I'm not going to go through this. You can look at this and pause it if you want to try these on your calculator. Sometimes it's helpful to solve problems by changing the base. For example, maybe we have a base 3 problem, and our calculator doesn't have a base 3 button, but it does have a base 10 common log or a base E, a natural log. And so we can find the value of any log by using the change of base formula. And this just says if, for example, if we wanted to know what the log base 2 of 17 was, we could find that on our calculator by using the log base 10 or the natural log base E. Okay. Notice what we're doing here is we're taking the log of the answer in whatever base we want to use it in or find it in, divided by the log of the base. The log of the answer divided by the log of the base. Now, the way I always remember this formula is that the base is in the basement of the fraction. The base is in the base of the fraction. So it's the log of the answer over the log of the base. Let's look at an example here. So log base 5 of 8 is difficult to figure out what the answer is because 8 is not a multiple of 5, right? So 5 squared, for example, is 25. 5 to the power of 1 is 5. So we know this number, this log is going to be some number between 1 and 2, but we have no idea what it is, and we don't have a log base 5 button on our calculator. So we can change it to the common base. Remember what we're going to do here is we're going to take the common log of 8, the answer, divided by the common log of the base 5. Okay, so we let a equal 10, b equal 5, and m equal 8, and we use the change of base formula. Log base 10 of 8 divided by log base 10 of 5. I encourage you to try this same thing with the ln button, and you're going to get the exact same answer. ln 8 divided by ln 5. You're going to get the same answer. And really, there shouldn't be a 10 here. These should just be log, because that you don't need to write the 10 there, because when there's no number, it is the common log. We can also use base E for a conversion. Oh, this is the exact same one. I'm sorry. I didn't realize I had 2 slides in here. And you can see we get the exact same answer. We do ln 8 over ln 5, the natural log of the answer, over the natural log of the base, and we get an actual value. All right. Graphs of logarithmic functions. Graph y equals log base 5 of x. Okay. Y equals log base 5 of x is equivalent to x equals 5 to the power of y. So one of the things we could do here is simply select values of y and compute x and create a table. And then we can plot the points, and again we see the log graph here. Your calculator will graph these, so I'm not really that worried about you graphing log base 5. Now what you could do, there is a problem here why you can't do this, because you don't have a base 5 log in your calculator. There is a function in there that will change the base to calculate it. I'm not sure you can graph that though. Graph each of the following. Describe how each graph can be obtained from the graph of the natural log of x. So what we're looking at here is translations. It says give the domain and the vertical asymptote of each. Okay. Before we start, I want you to notice this. X plus 3, the natural log of x plus 3. Now remember, we cannot take the log of a negative number. But this is only going to be a negative number if x is less than negative 3. If it's negative 4, then we get a negative number. But if x is negative 1 plus 3 is positive 2. So it's not what we're taking the log of. It's not that x has to be positive. In this case, when you have the log of an expression, it's whatever the argument, whatever's in parentheses here cannot be negative. So the domain of this function would be x plus 3 is greater than or equal to 0, and then we'd solve that. So it's x is greater than or equal to negative 3. So let's look at each of these graphs. This first graph is a shift 3 units to the left. The domain is the set of all real numbers greater than negative 3, as I just described, so from negative 3 to infinity, and the line x equals negative 3 is the vertical asymptote. Here we see a table of values, and here we can see the chart, and we can see the vertical asymptote at -3 because it's shifted 3 units over. This graph is a vertical shrinking of y equals ln x. Why is it shrinking? Because we're multiplying it by 1/2, followed by a reflection across the x-axis. Why? Because it's minus, and a translation up of 3 units because we have a positive 3 here outside the function. The domain is the set of all positive numbers, real numbers, because notice we're taking the log of x, and we have to take the log of x from 0 to infinity. Okay? Or greater than 0, I should say, not at 0. You can't take the log of 0 either. So we do a table, we do a function, and we can see that. The vertical asymptote and how it's shifted. All right. In a study by psychologists, Bornstein and Bornstein, it was found that the average walking speed in feet per second of a person living in a city of population P in thousands is given by the function W of P equals 0.37 log of P plus 0.05. The population of Savannah, Georgia is 132,410. Find the average walking speed of people living in Savannah. The population of Philadelphia is 1,540,000, etc. Find the walking speed of people living in. We've already got the beginning of the answer here. Since P is in thousands, it's really important you notice things like this in the problem. P in thousands. So the population here is in thousands, so we don't use 132,000 and plug it in for P. P is in thousands, so we use 132.410. Because this unit is already in thousands. So 132, if P equals 132, that's 132,000. All right? So that's key on these problems, is paying attention to the details. Then all we do is plug it in, pull out our calculator, and we get an answer. The average walking speed of people living in Savannah is about 1.9 feet per second. Go ahead and try the next one, or go ahead and hit pause and try the next one, and then you can check your answer. Here again, we're going to get, we have a 1,540,000, so that's going to be 1,540.351 for P. We plug that in, and we get 2.8 feet per second. All right, that's the end of our lecture today. Hopefully you enjoyed it. Hopefully you got some insight from that pause and are ready to do the homework.